Welcome back. So today we're talking about symmetric positive definite matrices. But first, I want to give just an example of computing eigenvalues. So let's assume that we want to find the eigenvalues of this matrix 3, 1, 1, 2. It's symmetric, and so we want to find the determinant of A minus lambda I and set that equal to 0. That's going to be the determinant of 3 minus lambda, 1, 1, 2 minus lambda is equal to 3 minus lambda, 2 minus lambda, minus 1 equals 0, and that simplifies to lambda squared minus 5 lambda plus 6 minus 1, so minus 5 is equal to 0. And from there, say lambda is equal to negative b plus minus square root of b squared minus 4ac all over 2 is equal to 5 halves plus or minus the square root of 5 over 2. And so there are eigenvalues. So how would we find the eigenvectors? Well, it's a slightly different approach, but once we have the eigenvalues, we can set up this equation, A times V, and we'll choose V1 is equal to lambda 1 times V11 V12. And here we happen to know what lambda 1 is, say 5 plus the 5 over 2 plus the square root of 5 over 2. So 5 plus the square root of 5 all over 2. And unlike the other one, I'm not going to push through this one. Essentially, this just is solve two equations with two unknowns, or as I mentioned last time, use Eig A in MATLAB. That said, finding the eigenvalue of a 2 by 2 matrix is a good thing to be able to do. It gives you some intuition for what's going on, and you can even solve it in the general case, and it's not too hard to do. Okay, we discussed last time that we can decompose a symmetric matrix in terms of its spectral decomposition, as shown there. Today we're going to look at the specific case of positive definite matrices. So let's go back to our definition font here. Definition: a symmetric matrix A is called positive definite if it has strictly positive eigenvalues. that is lambda n is strictly greater than 0 for n 1 to n. If it's not strictly greater than 0, we can call it positive semi-definite, as long as the eigenvalues are not negative. So greater than or equal to 0 for n ranging between 1 and n. Now, typically, and we will do this actually almost exclusively in this class, we assume that lambda 1 is greater than or equal to lambda 2, greater than or equal to lambda 3, all the way down to lambda n. So lambda 1 will be the largest eigenvalue. And this is just a matter of sorting it, putting things the way we want them to be. So why? I should note that in MATLAB, sometimes it returns them sorted, and that's really nice. But not always. In fact, often it does not. So you can't assume that they're sorted in MATLAB. And so if you extract the eigenvalues, you want to use some function that assumes you have sorted eigenvalues, you'll need to sort them manually to do that. Okay. So, for symmetric positive definite matrices, and we're going to simplify our notation here. For symmetric positive definite matrices, by the way, another way of saying that a matrix is positive definite is to say it's greater than 0. It's just a shorthand. This does not mean that each of the elements is greater than 0. It means that the matrix itself is positive definite. It doesn't say anything about the symmetry of it, so we're going to generally just mention symmetric positive definite matrices. So in that case, if you pick any matrix or vector x and multiply it like so, x transpose ax, and then normalize it by x squared, that's the same as saying choosing any x such that the norm of x is 1, x transpose ax, that's going to be 1, lambda 1, the largest eigenvalue. Likewise, the min of x transpose ax divided by norm squared of x is equal to the min, same setup here, any x in Rn such that norm of x is 1 of x transpose Ax. That's going to be lambda n, or the smallest eigenvalue. So, how do we demonstrate that? Let's see, I've just got a little room. Let's see what we can do here. We'll go with the max. If we have the max equation from above, get A transpose X. That's equal to the same max of X transpose V lambda V transpose X, which is just equal to the max of Y transpose capital lambda Y, where Y is equal to V transpose X, which is equal to the max. So what will be the norm of X? I'm sorry, norm of Y. Norm of Y will also be 1. Max of the sum of Y I squared times lambda I. Well, this is going to be maximized for y1 equals 1 and yi equals 0 for I not equal to 1. And so that's the sketch of that proof to show that this is the case. So this type of analysis, actually it'll come in handy for a lot that we do, but it's also a critical part of understanding and analyzing adaptive filters, which we will get to a little bit later in this class. So a few more things and one example about symmetric positive definite matrices. So let's see. So let's go through a quick example and see how this all works together. Let's say A is equal to 1/2 3 1 1 3. This gives us a V1 normalized of 1 1 and a V2 also normalized of 1 minus 1, and the associated eigenvalues are 2 and 1. So if we have A times X for some X, we can write that as A, or as V lambda V transpose X. And let's let X equal some linear combination of our eigenvalue vectors. Since the eigenvectors are orthonormal, that spans any possible x we would care to see. And now we can write this and just work out the math explicitly. 2, 1, 0, 0. So this is our v, and these are vectors here. So I guess I'll change that v2 like that, and now we have v1 transpose, v2 transpose, and this is times alpha 1 v1 plus alpha 2 v2. Well, okay, so v1 times v1 is going to be v transpose times v1 is going to be 1, and v transpose times v2 will be 0. So the right hand side of this is going to simplify a bit. We get alpha 1 there and alpha 2 there. And multiplying that through a little bit more, we now get v1, v2 times a single vector, 2 alpha 1 and alpha 2, which is equal to 2 alpha 1 v1 plus lambda 2 v2. So what happened here? This is a key to intuition with what's going on with these vectors. So right now, since we're dealing with the L2 norm, the standard norm, I guess I haven't specified that. I'll specify it now. We're dealing with this. This is going to be the set of all x where norm of x is equal to 1. And it's going to be spanned by two vectors. Who knows exactly where they'll be, but they'll be orthogonal to each other. So we're going to call this one v1, and that one we'll call v2. So when we do when we create some linear combination of those, as long as we do it such that alpha 1 squared plus alpha 2 squared is equal to 1, we're going to be picking some point on that. But when we multiply by ax, what's going to happen? Let's see. See if I can represent that well. Apparently not, unless I change something here. I'm just going to, for now, there we go. We're going to redefine our x vectors to say, or our eigenvectors, to say that's v1 and that's v2. So what happens is, as we choose a value of x, if we chose it directly aligned with eigenvector 1, it's going to stretch all the way out to that point. Whereas eigenvector 2, when multiplied by A, does nothing. It isn't stretched at all. So if the black represents x, then the green represents ax. And inasmuch as x is aligned with v1, it's going to be stretched by that factor of 2. Aligned with v2, it's not stretched at all. And if it is somewhere in between, it will be stretched proportionally as this one was. To the degree it contained alpha or v1, it will be stretched by a factor of 2. So something, say, right here is now stretched less than a factor of 2 and more than a factor of 1. And we can get that from the spectral decomposition, or representing x in terms of its eigenvectors. Just two other little points here. One is, when we're solving equations, back to our initial problem, y is equal to ax, and a is symmetric, positive, definite, then we already know that x is equal to a inverse y, because if it's positive definite, it will have an inverse. But we could also write that as x is equal to v lambda inverse v transpose, because the inverse of v, remember, is just v transpose in the case of real v Hermitian, in the case of it's not real. So x can be written also with a spectral decomposition, but now it's 1 over n y with vn times vn. So once we have the lambdas, the eigenvalues, and the eigenvectors, then the solution becomes simply a matrix multiply and a sum of vectors. So now this seems great, but the only problem is finding the eigenvectors and eigenvalues is as difficult as actually computing the inverse. But we'll just sweep that under the rug for now, because we can still use this for a lot of analysis, and it can be very, there are cases where we do happen to know those things. And also, there are cases when it makes more sense to go through the difficult computations of finding that, the eigenvalues and the eigenvectors, and then proceeding on to a solution. So we'll talk about one of those upcoming when we have observation error in our next matrix. Before I check out, one last thing. What are the eigenvalues of A inverse, and what are the eigenvectors? Well, if A inverse exists and it's symmetric positive definite, and in fact we don't even have to go that far, but we could see that as long as it exists, we have A times Vn is equal to lambda n Vn. From there we can say Vn is equal to lambda n A inverse, because we've already stipulated that that exists, times Vn. And that will give us 1 over lambda n Vn is equal to A inverse Vn. And so the eigenvalues of A inverse are 1 over the eigenvalues of A, and the eigenvectors are the same as the eigenvectors for A. So that'll do. Thank you. Talk to you later.